Welcome to Power System Protection Lectures. My name is Pratap Mysore. Today we will cover protection of rotating machines. Rotating machines, I'm looking at motors and also synchronous generators. Synchronous generators, they convert mechanical energy or rotational energy into electrical energy. So prime mover is there, which provides the rotational energy, and this is used to produce megawatts, the active power. We also need DC field excitation to keep the voltage up at a nominal value, and this provides the DC excitation provides the reactive power that is generated by the machine. If steam is used for the prime mover, then these are steam generators, and then they can be as large as 1200 megawatts, 1200 MVA, and the steam is generated by coal or oil or nuclear as the fuel, and we also have refuse derived fuel for a little lower MVA rated generators. Water is also used to provide to get the rotational energy. These are hydro generators. They can be as large as 800 MVA. And then we also have combustion turbines, which provide this. And then if a combustion turbine is, they are as large as 300 megawatts, 300 MVA machines. And below this, we have diesel generators. They also generate power up to 50 MVA. And diesel generators are normally directly connected to the system. Steam generators, they are run at very high speeds. Therefore, these are cylindrical rotors. They don't have any projections or poles as in the salient machines, and they are 1800 to 3600 RPM. And then if the steam content is high, heat content is high, they run it with lower poles at higher RPM. That is 3600 RPM. Salient pole machines, they run from 100 to 600 RPMs, rotation machines. As I mentioned, diesel generators, they are up to 50 MVA. They don't have any voltage step up for that. They are directly connected to the distribution bus or a 13.8 kV bus in this case, if you look at it. But whereas larger machines, they connected to generator step-up transformers so that the power is directly connected to the HV or EHV systems. Generator grounding affects really what type of relaying we use for generator ground faults. If the generator is connected to an ungrounded system and generator itself is not grounded, the fault current is zero for stator ground faults. And then, but what it does is it imposes face-to-face voltage on other two terminals, and then that might cause insulation failures. And then the generator terminal voltage could be high also due to ferroresonance. Because of the capacitance associated with the bus duct, any transients, there is no damping. So that also provides very high transient over voltages at the generator terminals if the system is not grounded, if the generator is not grounded. The generators are also grounded through low impedance in some cases, and then the high impedance grounding is very common in very large machines. A high impedance grounding is you're connecting the neutral of the generator to the ground through a very high impedance. Instead of connecting a direct resistance of that value, a transformer step-down transformer is used there, and then the resistance is connected on the low voltage side of the transformer. So that reflected resistance on the high side will be transformer turns ratio squared times the resistance connected on the low side. And generally, a value is selected so that your current is limited to 5 to 25 amperes for any stator ground faults. Low resistance ground is generally limits the current to 200 amperes or 150% of the generator rating. And typically these are used where there are a group of generators connected to the system via single step-up transformer. Low reactance grounding is also used in the system. Generally, these are generally used on generators which are directly connected to the distribution network, like we mentioned, 13.8 kV, 50 MVA diesel machines. And these reactance grounding is used. The reactance value is also selected in such a way that the X0 to X1 ratio is 3 or less. This will limit the voltage on unfaulted phases for a single anti-ground fault to less than 125% of its nominal. Uh, Currents during generator faults, when you take a generator and put a short circuit, three-phase short on the generator, it goes to the fault current will be very high initially, decays very fast in 3 cycles, and decays at a much slower rate for about 8 to 10 cycles. Then you get steady state current. The first portion is called the subtransient reactance. The current is due to the subtransient reactance, and then this is called the subtransient period, and then you get transient period, and then the steady state period. Generators are highly reactive, so they are very high X over R. So this produces very high DC offsets initially. And current continues to flow in if there is a fault within a generator, even if you disconnect it from the system because of the rotational inertia of the machines. So we have various types of faults as listed here, and then we use protection to detect all these kinds of faults. The first one is the stator fault, and then the field ground fault is the second one, and then abnormal frequency protection, because these generators are supposed to run at 60 hertz. You don't want them to be running lower or higher. That is all. If we use it for that. Loss of field protection in case if the field breaker opens, then you are not generating reactive power, or it is not providing it. It absorbs the reactive power from the system, which we will cover all these things. I'm listing it here. Then we have a standard thermal overload protection, or just through overcurrent relays. And overexcitation protection is also used if the frequency is low and the voltage is high. And reverse power for inadvertent energization, we use directional overcurrent relays or reverse power elements for that. Negative sequence protection due to effects of system unbalance. This is also important for us. And loss of synchronism during faults, it might go speed up and then we lose synchronism. That is also used that is also detected by the protection function. So if you look at various functions that are associated with the generator protection, they have distance relay, which is looking from the neutral of the generator all the way into the system. And then we have volts per hertz, which takes the ratio of the terminal voltage to the frequency to determine the fluxing in the generator core and also in the transformer core. And then if the ratio is very high, then it gets saturated and creates produces generated. It is the result is overexcitation, which is reducing which results in overheating of the cores. You have undervoltage detection 27. 32 is a reverse power. The numbers are all IEEE designations for different functionalities of the protection. Loss of field is if the field breaker opens, then that is also detected by 40. 41 is the field breaker protection. 46 is negative sequence. 51 is time overcurrent. Voltage regulated overcurrent constrained or controlled overcurrent relays are also available. Field DC protection 53. 59 is the over voltage. 60 is the voltage balance. And then 64 is the field ground detection. And you also have 100% stator protection. We inject some other frequency than 60 hertz subharmonic and then monitor the current and the signal coming out on the phase terminals when it is injected from the neutral terminal. And then we find out if there is any stator fault. Loss of synchronism relay is also available. Function is also available. Then you have frequency, underfrequency, and overfrequency protection is also used. Then conventional protection like transformer differential, generator differential, and then overall differential, 87U we call this here, which protects both transformer and generator within the zone of its protection. Then 63, 70, 71 are used in the guide for gas detection and oil level functions. C37102 is the guide for the generator protection, and they go through in detail about functionality of these and also on how to set this. That is an excellent guide for reference. There are a lot of Application guides are available from North American Electric Reliability Council, which has taken interest to make sure the protection is set right due to recent disturbances or 2003 blackout that resulted in the failure of power in the East Coast. There is also a turn-to-turn fault protection. They try to use a differential scheme shown here from the neutral side to the phase side. And then this is one of the new functions that has been added. We also have backup relaying for the generator winding faults. So you have a distance relay looking from the high side into the low side, and that could be set to detect faults in the system. And also the traditional 87U, the overall differential for the generator transformer, also provides protection for that. Stator ground fault detection is used. Differential relay sensitivity depends on the type of the grounding. As I mentioned earlier, separate ground protection scheme is used for that. Differential and then if it is a high impedance thing, we don't have not much of differential current, we cannot detect it. Based on the third harmonic measurements at the terminal and neutral, this is another method that is used. They look at the generated third harmonic voltage on the neutral and also at the bus. And then if there is a fault near the terminal third harmonic goes down, and then the neutral side increases. And it's vice versa. If a fault is moved towards the neutral, the third harmonic content at the neutral side also goes down. The 100% stator fault protection is you inject a subharmonic frequency in the neutral and measure it on the phase side, and then you just compare. If there is a ground in between, then there is a loss of signal, and this is detected. I'm just giving you these functionalities because I'll be making. I will not be making a cover. I will not be able to cover all the functionalities and explain to you in detail. Please refer to the application guide C37102 from IEEE that provides a lot more details into this. Other function that is used is field ground protection. DC field circuit is typically ungrounded. A single ground gives it a trip or alarm decision. It depends on the utility and the system and also the entity which is running which owns the generator. Two grounds cause an unbalance in air gap fluxes that results in machine vibration. We can also look at the vibration and then detect that, and then it might also result in a lot of damage. Backup protection for this electrical ground fault detector here, they use vibration detectors. And recent microprocessor relays have other functionalities which looks at the ratio of the negative sequence voltages on the stator side and determine where if there is a fault on the stator or the ground on the rotor. Abnormal frequency is extremely important on the steam and gas turbines because steam machines they have at frequencies little lower, little less than the 60 hertz. They run into mechanical resonance regions. So you want to avoid that. So steam machines are generally tripped before we hit those mechanical resonant frequencies. And these frequencies are also frequency detection is also coordinated with the system, so that if there is any system unbalance, under frequency event, you don't want the generators also to drop out, because frequency of the system goes down if the load is greater than the generation, and under such conditions you don't want the generator to drop off. So they are set higher than generator under frequency trip settings. Accelerated aging and thermal stress is very common on the rotors, on the turbines, and that is why you're setting under frequency protection. Over frequency is more of a mechanical device, and then they can use either electrical or they have overspeed devices that take care of tripping the generator. The curves are given here by the manufacturers. These are called capability curves for turbine over and under frequency. And if you look at it, 61.8 to 57, if anything above that or below this, it is prohibitive region. And then the 0.1 minutes you can run from 57.5 to 57. and this is essentially you try to trip the generator in 15 cycles if you hit these frequencies or instantaneously at these frequencies. Hydro turbines is not an issue. You can run at lower frequencies or higher frequencies because there are no resonance issues associated with that. And generally, it should not be used on hydro turbines. In 1996, there was an event in the western region of United States. There were several hydro units that tripped because they were set, under frequency relays were set on that. There is no need for that to set it on the machines. And over frequency is also not a problem, and it could be used as the backup devices like overspeed devices, which closes the intake, emergency intake gates are used on the hydro machines. Volts per hertz, essentially, if you take the ratio of the voltage to the frequency at which it is rotating, it provides the flux, electric flux in the core of the machine. So the generator and transformer manufacturers provide curves, and then we have to set the relays below that to prevent hitting those limits. Normally, transformer rating will be different from the generator rating, typically 95 to 100% of that. So you have to make sure that you are addressing both these issues. If you look at a transformer, you can load up to the voltage can be at 105% of its nominal rating, and then still we can push 100% full load. If the voltage increases to 110%, we have to take off all the loads and it can be run only at the no load. These curves are provided by the manufacturers. It is important to have that. And then if you look at this, both of them are adjusted to the same voltage base. Here you have a generator at 24 kV, transformer is set to 22.8, multiplier is 0.95 for the transformer curve. And then you look at the generator curve, and then you look at the transformer curve, you set the protection so that it is below any of these. So you are not reaching the limits on both the transformer and the generator. There is a chance that the machines will be on rotating air when during outages, or when the machine is running. Suddenly, if you close the steam valve, then there is no prime mover input. The generator is connected to the system, so it consumes megawatts from the system, and the field is still connected, so it still generates megawatts. But because we took away the prime mover, the machine starts absorbing, consuming a lot of megawatts. And then this is very dangerous for steam machines because steam is churned at that high speed, 1800 or 3600 RPM on the machines, and this produces overheating of the turbines and severe damage to the turbines. So they use reverse power element to take the machine out of service. They are typically set to 0.5% of the generator rating, and time delay set below the maximum allowed time specified by the manufacturer, typically 30 seconds or less. European users have used low forward power. When the machine is already generating, they try to set a low forward power. If the power hits that particular value, then it takes the machine out of the it trips the machine and disconnects it from the system. Reverse power is not used on the hydro machines because they are much more robust, so there is no need to use that on that. There is inadvertent energization, is directional overcurrent relays, or 50 voltage supervised by 27 is used. This is accidental closing of the generator breaker with the generator on the turning gear. Normally during outages, generators are put on a turning gate, so it is rotating at very low speed. And then by mistake, if you close the generator breaker, you are accidentally energizing this. So flashover across the open contacts is also one of the reasons. Even though the breaker is open, it can flash over, and single phase energization takes place and produces severe unbalanced currents. So their damage is very high. So the generator is now started as a motor because there is no prime mover, and then it produces local excessive heating on the rotor also. and the current can be as high as 3 to 4 times the full load current, and the voltage is dipped to 0.5 to 0.7 of the nominal. Okay, and in a weaker system, it could be 2 times the rated current at voltages at 0.2 to 0.3. So overcurrent element is set to 50% of the current seen, never set less than 125% of the I rated, and voltage is set to 50% of the phase to ground voltage with a delay of 15 seconds. It disables 50 element, and directional overcurrent relays have been used IA and VBC in the previous cases. That is 67 here, as it is mentioned. I know that we are going through very fast, but I'm just wanted to see different to just inform you that there are various protective functions used on the generator. It is a lot more than any other protection what we have covered so far. So I just wanted to introduce you to you, and then you can go back and look at C37102, the applicable the generator protection guide. And there are several papers published by North American Electric Reliability Council. You can look at their website, nerc.com, and then you can get those papers in compliance region. There is also an overcurrent protection, 51V. It is voltage controlled or voltage restrained. When at normal voltage applied to the relay, the pickup is set to 200% of the rating, and then provides a backup for system faults. And here, as the voltage goes down, then the pickup reduces as the voltage also reduces. That is, system voltage reduces. So under fault conditions, the relay sits up at 50% of the rated current. Under normal operating conditions, it will be well above 100% of the rate of the generator current. Unbalanced protection, if there is a system unbalance, it causes negative sequence currents to flow through, and this causes overheating of the rotor. The rotor is rotating in counterclockwise direction at synchronous speed, 60 hertz, and then you have a negative sequence input on the stator, which is rotating in clockwise direction at 60 hertz. So it induces currents at double the frequency on the rotor. And then there are limitations on this which causes overheating. And so IEEE standard 5012 and 5013 provide you with withstand capability curves for the generators, and the time for the withstand time also, or duration of how long it can withstand these types of unbalances. I squared T capability curves are produced. I squared T equals constant. I2 is your per unit, I2 square T, and not I squared. It is a negative sequence current. And then K is around 40 for salient machines, and decreases from 10 to lower values on directly cooled MVA machines beyond, which increases beyond 800 MVA. So this is provided by the manufacturers and also provided in C50.12 or 13 standards. And then you have to set the relay so that the curve of the relay is below that. The conventional system relays, here is another example. As I mentioned, that the standard says 10% of salient machines, and for otherwise it is 5% is a permissible negative sequence, and 10% to 5% on cylindrical machines, lower values at higher MVA. So if you look at it, you have a machine curve, I2 square T, and then you have the relay which is set below that. In electromechanical relays, it was a function of how much load is there. In digital relays, you can set just a more sensitive function, so it provides much better protection, as mentioned here. Undervoltage relays, they work, generators work within plus minus 5% of their rated voltage. Undervoltage relays are set at 90% of its nominal rating, and they are provided with a very long time delays. This is to coordinate with the system faults. If there is a system undervoltage, you don't want these to take the generators out. And then at 80%, it is set to 2 seconds. Instantaneous is typically set to 70%, but still, because of the system configuration, this terminal voltage can vary and we have to run the studies before we set the instantaneous. Otherwise, you have time overcurrent and definite time settings are used for undervoltage relays. Loss of field protection, accidental opening of the field breaker results in the machine which is connected to the system consuming a lot of reactive power. As I mentioned before, the prime mover provides the megawatt output, and the steam input higher provides the megawatt input if steam is one of the inputs for the prime mover, or megawatts is generated by the reactive power. So when the field is removed, it consumes a very huge amount of the reactive power, which results in lower voltage at the terminals, and also it could be and the generator rotates at super synchronous speed. It works as an induction generator under such conditions. There are capability curves which are provided here of how much the generator can provide reactive and then active power. And then you also have a steady state stability limit that under normal conditions, how much output it can provide. And then there is an underexcitation limit. These are various limits which are provided by the manufacturers. You have to make sure that you don't exceed any one of these, and then the protection settings are not limiting the operation of the generator. This is a big thing in National North American Electric Reliability Council, PRC 025, and there are other PRCs, reliability standards for compliance and protective relay standards, compliance standards, which provide very detailed analysis on how to set this and what to do. So again, as I mentioned, C37102 provides a very good explanation of all the protective functions, and whereas NERC provides a lot of details on how to set it and what to check for and how you can prevent misoperation for a fault which is not inside the generator. Loss of field, which results in very high reactive consumption. Essentially, the relay looks at it as in the negative region, in the RX region, which we covered in distance relays, and then increased loading. The reactive power under normal conditions, if it is here, it tries to come into these characteristics of the distance machine, and you have steady state limit here, and then under excitation limit is also here. Outer step is another protection used when a fault occurs in a system. The electrical output of the generator comes down. You still have the mechanical input, so the generator speed up. And if the fault clearing is delayed, it tries to gain momentum. When a fault is cleared, it tries to control back, but because of the high inertia of the machine, they try to speed, and it may go out of step, and then it might slip a pole. So it is important for us, for a mechanical device, not to prevent mechanical device from suddenly getting into a jerk, which results in multiple pole slip. So it is very important for that. And then we use impedance measurements using blinders to detect these kind of faults. And so in short, I did try to just tell you what types of protections are used in the generator, but I have gone through it at super synchronous speed. This itself could be a weak course, but I'm trying to cover and then let you know the different types of protections used on the generator in half an hour. So the references are here. A guide for ground fault generator ground protection is 101. 102 is for AC generator protection. 106 provides abnormal frequency protection, and 50 and 5012 and 5013 give you the negative sequence capabilities for the abilities for the generators. And there is an excellent paper on Beckwith, one of the manufacturers' papers, about power plant horror stories, which tells you how the relays were not set and then what resulted in excessive damage of the generators. So with this, I will stop here of just covering this. In the next subsequent lecture, we will cover the motor protection in brief and discuss what functions are used for protection of the motor. Thank you.